Yes, any other questions?
Yes, if we imagine a shell, a vector shell, we said that charges move to the surface. If we put a charge
inside the conductor, then they go to the surface.
Yeah. But why does it go to the inside surface? Why does it always go to the outer surface?
Because by using Gauss' law, we have proven that the electric field, okay, there are two things. One is the electric field inside a conductor in statics. I underline this. Only in statics, in electrostatics, the electric field inside the conductor should be zero. If it is not zero, the charges in the conductor will be feeling a force, and since they are free to move, they will be moving around. That is not statics. Only in electrostatics, inside the conductor, there can be no electric field.
So the cavity inside the conductor must also have an electric field as well?
Now, the cavity, if you imagine such a cavity here, inside the cavity, you can have electric field. There is nothing that prevents that. Because our argument is based on the fact that we are only dealing with systems in electrostatics. And secondly, in electrostatics, the charges should not be moving, and hence they should feel zero electric charge. There should be zero electric field inside the conductor. This is not inside my conductor. This is just a cavity. This is inside my conductor.
So are there any charges on the inner surface?
On the inner surface, there can be charges on the inner surface if I put some other charges in the cavity. Because if you imagine such a Gauss surface, the total charge of this surface plus the total charge inside the cavity, it should be zero. Because there is no electric field in here. And since I choose my Gauss surface completely in my conductor, the electric field everywhere is zero. So the integral of electric field on my Gauss surface is again zero.
But one fine point of this. Coming back to the shell, if I just put plus Q charge in it, the plus Q charge will be concentrated outside, right? And there is no charge on the inside of the surface.
Potansiyeli gelirken bir work ile bir charge'ı alıp yakınlaştırıp work ile hesaplamıştık. Fakat onun potansiyelle Q çarparak da aslında U'yu, yani delta U'yu hesaplayabiliyoruz. Ama hangi Q ile çarparak? Yani work'te bunu define etmek kolay ama
Now, there are a couple of distinctions, just like in the case of the electric field. Remember, we had to make certain distinctions. We define the electric field as the force that a charge feels divided by the charge of the charge, with the test charge that we put over there, and we assume that the test charge is very small. Now, I can talk about the electric field created by these four charges. Q1, Q2, Q3, and Q4. I can talk about the electric field created by these four charges at this point, let's say. And then if I bring a fifth charge over here, the force that that fifth charge will feel will be given by E times Q. That is the fifth charge. Now, the force that this charge feels over here is Q4 times the electric field at that point, but created not by all these four charges, by only these three. Because if you just calculate the electric field created by these four charges, including this one, at this point you will find that it is infinite, because every charge, the electric field created by a charge at its position is infinite. It is the 1 over r squared. If you just put r equal to 0, that's infinite. So the force you can always calculate as Q times the electric field created by other charges. The same thing applies for the potential energy and potential. Again, you can imagine as many charges as you like. Now, if you bring a fifth charge from infinity to here, this is Q5 from infinity. up to this point, the change in the potential energy of your system will be equal to minus Q5 times E dot dl. Now, this Q times E is nothing but the force that is exerted on this fifth charge by the other four charges. And the change in the potential energy, if you bring a fifth charge, you can also write it as Q5 times V. Let's say this point is P, V of P. This is the potential created by the other four charges. This doesn't contain the potential created by the fifth charge.
Kafamı karıştıran şey şu oldu aslında. Gördüğünüz soru defter yapraklarını çevirir gibi plate'leri aslında kapatmak için ne kadar work gerektiğini soruyor. Peki orada area ile çarptığımız total Q'yu potansiyelini çarptığımız.
I didn't understand the question.
Elimizde 3 tane plate var fakat şeyleri aynı yerler ve onları birbirlerine kapatmak için uygulamamız gereken
Let's just calculate two of them.
yani orada kullandığımız Q'yu area ile mi çarpalım?
Let's do two of them. And then we will see. Let's just imagine we have this plate of charge plus sigma. We have this other plate of charge minus sigma. Initially separated by a distance d, and let's say that they have a finite area, very large but finite area A. And let's say that we will be moving this plate towards this minus sigma plate. Now, there are a few things we can calculate. First of all, what is the force that we have to exert? The magnitude of the force. Let's ignore the signs for the time being. What is the force that we have to exert on this plate to be able to move this with zero acceleration towards the other plate? What is the force? How much force we have to exert?
Amount of the force they exert on each other.
So which is? What is the electric field? Electric field is sigma over epsilon 0. And the charge we have over there, this is the electric field, sigma times A. This is E. This is Q. Do you agree? The others, do you agree? I don't. You see, what is the sigma over epsilon 0? The total electric field, the electric field created by this one plus the electric field created by this one. But if you want to calculate the force acting on this one, we have to calculate the electric field created by other charges, in this case by this plate. And if we have a single plate, the electric field created by this single plate will not be sigma over epsilon 0, but it will be sigma over 2 epsilon 0. So this is the force. Well, this is just a constant force. And if we just move this plate under the influence of a constant force by a distance d, the work that we have to do will be sigma over 2 epsilon 0 times sigma A times the d, the force times the distance. Now, the work that we do, is it positive or negative? You see, there is already this force that these two plates are attracting each other. So the force that this plus sigma plate is feeling due to this minus sigma plate is pointing downward. Well, if we want to move this very slowly with zero acceleration, we have to exert a force in the upward direction. The force that we exert is in the upward direction. The displacement is downward. That means the work done by us is minus this one. Minus sigma over 2 epsilon 0 times sigma A times d. This is the total work we have to do if we want to bring one plate to the other one that are separated by a distance d.
Why the force is upward then?
Well, this is the force that we exert. There's already a force acting on the plate in the downward direction, so we have to somehow balance it to prevent this plate from acceleration. And if you want to allow it to accelerate, then of course you don't need to apply the same force. But then we have to know, to determine how much force we are applying, we have to know the acceleration, etc. I hope your question was not this one, by the way. I mean, in this case, how much force do you need to exert to just close this one? Well, I personally don't like those questions. I mean, I don't think they, of course, I mean, it's nice to be able to calculate that. Eventually, you have to be able to calculate that. But I don't think that really contributes much to your understanding of the subject. Well, in certain cases, yes. In certain cases, not. So first, you have to prove that you can calculate by just considering the middle point. In this case, it will be valid, but not in the general case. Since the force is uniform, there are lots of simplifications. But if I just tell you that, okay, you can just take the central points, then you will just go ahead and calculate by using the center point for all problems in which it's not applicable.
Can we analyze the quadrupole situations, potential?
Let's just assume, take such a case. And we had already considered the case when we have a plus q and a minus q without the other charges. It was, I think, in one of your homeworks, if you calculate the total dipole moment of this one, this system is nothing but a plus q here, a minus q here, another minus q here, and a plus q here. This is a dipole with a dipole moment in this direction. This is another dipole with a dipole moment in that direction. The sum, the total dipole moments. This is equal to 0. So this doesn't, I mean, these dipoles and quadrupoles are in a sense some models of the charge distribution. For example, we know that for a hydrogen, for a water molecule, it has a dipole, and most of the time just treating it as a single dipole is enough to understand its properties. But for certain other molecules like the carbon dioxide, which is linear, we have a carbon here and oxygen on both sides, such a molecule doesn't have a dipole moment. So if you want to understand its electric properties, just using dipoles wouldn't be enough. So for the carbon dioxide, you need to consider such a configuration. Plus Q, minus 2Q. This is our point. Let's say this is R. This is R plus, or let's call it at R1. This is R2. Now, you don't like vectors still. It will be quite easy to solve this problem using vectors. We know the potential already, V at this point P. This will be Q over R1 plus Q over R2 minus 2Q over R times 1 over 4 pi epsilon 0. This is the potential. So there is nothing to write this one, but we would like to express this potential in terms of this angle theta and the distance r if r is very large. And let's say this distance is d, this distance is also d. Now let me imagine this R1 vector. Now the R1 vector, this one pointing from here to here, is nothing but minus d in the z direction. Let's call this one the z direction, plus the r vector. This is what R1 is. R1 squared is nothing but the square of this vector, which is, no, this is not R hat, that is just the R. No, nothing is in parentheses. No, this expression is in parentheses, but nothing here. Minus d times z is this vector over here. This r vector is this vector over here. Now, R1 squared is just r squared plus d squared minus 2 dr dot z hat. But I know what that scalar product is. R squared plus d squared minus 2d. Now, this is our 2dr. And the angle between r and z hat is pi over 2 minus theta. So there I get a sine theta, or cosine pi over 2 minus theta. So R1 squared is equal to r squared plus d squared minus 2r times d times sine theta. Okay, this is one part. Now let's look at this R2 vector. R2 vector is this vector over here. It is nothing but, again, minus d times in the z direction. No, sorry, d in the z direction plus the r vector. That is what R2 vector is. D in the z direction plus r, and R2 squared is equal to, well, the only difference is that this sign is different. That would mean this sign is over there is different. So R2 squared is just r squared plus d squared minus 2rd sine theta, plus 2rd sine theta. So we know R1, we know R2 in terms of theta and r. Again, up to this point, everything is exact. Now, what do we need? We need 1 over R1. 1 over R1. This is equal to r squared plus d squared minus 2rd sine theta to the power minus 1/2. This is equal to 1 over r times 1 plus d over r squared minus 2d over r sine theta raised to the power minus 1/2. I just factored out this dr squared, which is large. So that gives me 1 over r due to this exponent over here. The remaining is still inside this exponent. This is equal to 1 over r, 1 plus x to the power minus 1/2, where I defined x to be d over r squared minus 2d over r times sine theta. This is my x. Now, why did I call this one x? Well, I'm already told that I'm interested in a region where r is very large, d is small, so d over r is a very small number. D over r is a very small number, so x is a small number. So I want to calculate 1 over the square root of 1 plus x when x is a small number. Well, that is where the Taylor expansion comes into the game. So since x is small, I can expand this function around x equal to 0. So this will become 1 over r, 1 minus 1 over 2x plus minus 1 over 2 minus 1 over 2 minus 1 times x squared over 2 plus the remaining terms. This is the dipole approximation, which will give you 0 if you just ignore the other ones. This is what will give you non-zero. And then you do the rest. So this is x, you already know. Just put it over there. Ignore everything that is d over r cubed in the expansion. and then you will get the result. Do the same for R2. It will be just changing this sign in X.
Peki hocam bize bu anlattığı şey onun davranışıyla ilgili. Yani onun aynı zamanda bir point charge olmasıyla ilgili.
No, I mean, you see, what we are dealing here is most of the time in this course, what we will be discussing is given the charge distribution, what is the electric field, what is the potential? That will be most of the questions we will be asking you. Given the charge distribution. But how do we know the charge distribution to start with? In real life situations, in cases we want to understand what is going on over there, we don't know what is going on. We have to make some measurements over there. We have to classify it, we have to describe it somehow. So how do we determine the charge distribution? What we do is if we have very crude equipment, if we cannot make precise measurements, the only thing we can measure will be the total charge. If the total charge is 0, we will not be able to measure anything if our equipment are not precise enough. Let's say we have more precise equipment. In that case, we will start to measure whether the dipole moment is 0 or not. If it is 0, or if we have very, very precise equipment that would allow us to separate the dipole contribution from the quadrupole contribution, then we will be able to tell what the quadrupole is. Now, what this tells me is the total charge is the total charge. The dipole tells me how the positive and negative charges in my system are separated. So if the dipole moment turns out to be 0, it just tells me that the center of the positive charges and the center of the negative charges, they are at the same point. Now, if the quadrupole moment is non-zero, but the dipole is 0, let's say, it will just tell me that either the positive or negative charges in my system is a bit elongated, symmetrically. It doesn't create a dipole moment, nevertheless it creates a quadrupole moment like this one. Now, we usually don't start from the charges and go to the potentials. What we do is we measure the potentials. And we try to describe the potential in terms of either the monopole, that is the total charge, or the dipole, or the quadrupole, or we ask how much do we need, how many of them do we need? There are infinitely many, so-called multipoles. So what we can actually measure are the multipoles. And then the question is, from this multiple information, what can we say about the charge distribution that we are studying? Now, at this point, I agree that this problem, this quadrupole moment, it's just some mathematical exercise, nothing more. Those kind of things I can easily give in the homework. You have to get used to those mathematical manipulations. But the thing is, how do you interpret those things? How do you interpret your measurements? Of course, such questions we will not be asking in the exam. They are not easy to ask, not easy to grade. But that is the main point, although we are not asking it in the exam. Your main purpose shouldn't be to get high grades, but to be able to understand the tools that you can use to understand a given unknown system. Okay, other questions? I'm not continuing this solution because I don't think most of you will be following anyway. Well, you see, the thing is, if you have realized, I'm not really solving that much questions. I don't want to. If you have your question, what is it that you don't understand, then we can discuss that. That is what I would rather concentrate on.
I didn't understand that there is a system on it, there is two charge, and there is in a capacitor.
Okay, is it a capacitor or point charges?
No, it's not point charges. It's a capacitor, and you do a work with a charge that içine bir charge koyduğunuz zaman değişimi nasıl ölçebileceğinizi.
So we bring a charge over here.
Yeah.
From where? From infinity, okay. And what would you like to calculate? The change in the potential energy of the system. So how do you calculate this change in the potential energy? In general, not for this problem, but in general, how do you calculate the change in the potential energy? Work done. Okay, so it is minus F dot dl from infinity to that point. So what is this force F? Q dot E. So where is this E? So that's only in the capacitor, okay. Well, you see, if you say only in the capacitor, so there will be only force in this region. So what is E dot dl in this region? I'm moving horizontally. E dot dl will be 0. So the change in the potential energy in this case would be 0. Our conclusion would be that. Now there's one problem though. In this question we ignored the fringing effects. We don't know whether they will contribute or not. So I would rather try to find an alternative means of calculating this work done that doesn't necessarily ignore the fringing effects.
We can calculate it by measuring the total potential energy of the minus the potential.
Okay, how do we calculate the initial and the final potential energies? Well, let's do something else. Delta U is equal to Q times minus E dot dl. Now, what is E dot dl minus E dot dl? This is the point P. This is the point at infinity. So this is the potential difference between the point P and the point infinity. Now we have to calculate the potential at the point P and the potential at infinity. Now the easiest thing to do, we can set, if we can set the potential at infinity to be 0. Now if we choose such a path, there are some fringing effects over here, which we don't know. So such a path to move from infinity to this point P, okay, it will be correct. There's nothing wrong if you can calculate it, but without making some additional assumption or some additional calculations about the fringing effects over here, we cannot really calculate this one. But if the point P is sufficiently far away from the endpoints, and this thickness is sufficiently narrow, so that in this region, I can assume that the plate is almost infinite. Furthermore, the fringing effects will be only significant in this region. So I can choose a path which avoids this region over here, where the fringing effects will be important, and this region over here, where again the fringing effects will be important. So I can, rather than choosing such a path, I can choose such a path. Avoid these end regions. So if I choose that path, choose this alternative path to the point P. Now this, let me also call this point A. So the change in the potential energy of the system will be Q Vp minus Va plus Q Va minus V infinity. Now, what is the potential at the point A? Because we can calculate this one now. It is just the electric field times this distance. That's the potential difference between these 2 points. But now the problem is, what is the potential of the point A? Is it this, do you set up your system so that the point, this plate and infinity have the same potential? You can. There's nothing that prevents that. You can set up your system such a way. Or you can set up your system such that the upper plate and infinity has the same potential. But this, again, depends on your setup. Well, this is where we have the grounding, which we didn't really discuss that much. I mean, the potential at infinity, or sometimes we set the potential of Earth itself to be 0. That is the common choice. We had said that if you look at a sphere, an isolated sphere, we had already calculated that the capacitance of an isolated sphere capacitance is, do you remember? It should be 4 pi epsilon 0 times R. I might be remembering some factors wrong. But the important thing is that the capacitance of a sphere is proportional to its radius, of a conducting sphere. Now, Earth is a conducting sphere, basically. Since it has all these minerals, humidity, water, etc., it's conducting. And it's a large sphere, so the capacitance of Earth is infinite, which basically means that no matter how much charge you put on Earth, its potential doesn't really change much. You see, if you remember the definition of the capacitance, Q is equal to C times delta V, or delta V, the change between the endpoints of the change between the endpoints of a capacitor, the change of potential. This is equal to Q times C. Now, for a sphere, what we said was, the sphere, you can think of it as 2 conductors, one sphere, another conducting shell outside the sphere, but this shell is at infinity. So the difference in the potential between these two things, the shell at infinity and the ground, which is the Earth itself, which is a huge sphere, the change in the potential would be Q, how much charge you put on Earth, but C is infinite, almost infinite. So the ground has the same potential at infinity. So you can create such a system and ground the bottom. This is how we show it. Okay, the bottom plate might be grounded. Or you can ground the top plate. It's up to you. It depends on how you set up your system. If you ground both the top and the bottom, then there's no charge anywhere. So there's no potential difference, etc. Why are equipotential lines important? Well, if you want to use them, they are important. If you don't want to use them, they are not important. Well, for example, the surface of a metal is an equipotential surface. Of a conductor, sorry. The surface of a conductor is an equipotential surface. That is one information we have. The other information we have is the electric field lines are always perpendicular to the equipotential surfaces. Just combine the two and you can say that the electric field lines are always perpendicular to conducting surfaces. Again, in electrostatics, I repeat. Everything we have done, we have said up to this point are valid only if we are studying problems in electrostatics. We will see some of our comments that we have said here until this moment, we will see that they don't hold, they are not true when we move out of the domain of electrostatics. But in electrostatics, they will be true. And in electrostatics, the electric field lines should be always perpendicular to conducting surfaces. Now, a given definition, why are they important? Well, I don't think that's a justified question to ask, in the sense that what we are doing throughout this semester are just developing various ways of studying the same phenomena. We did it in 109. I mean, all the phenomena that we discussed in 109 was using Newton's dynamics, applications of Newton's dynamics, and nothing else. Angular momentum and applications of Newton's dynamics. Rotational objects, applications of Newton's dynamics. They simplify our treatment in some certain problems. They are not useful in other problems. The same principle holds here also. We are studying one phenomena, the behavior of electric charges, and we will be devising different means of describing the same phenomena. The Coulomb law is one way of describing the properties of electric fields. We don't need the electric field. We don't need the Gauss law. We don't need the, I don't know, whatever, the conductors, etc. You can develop everything starting from Coulomb's law. It will be difficult for you. We can do the same. Some of the problems we can study easier using Gauss law. Some problems we can study more easily using the electric field lines. Some of them will be easier to use to describe using equipotential surfaces. It will be just depend on your phenomena, depend on your understanding. You might feel more comfortable describing everything using equipotential surfaces. So your friend might be more comfortable describing the same phenomena using electric field lines. It's up to you. We just give you the tools, and you should be able to use at least a couple of them.
If you have a number shape of conductor, and we are saying, I read in the lecture that the side that has some kind of
You say, tell me your system.
any random shape of conductor.
One conductor.
Yeah, you're saying that the small surface area of that has a high distribution and one which is more on the side has the distance.
You mean such a surface. And we are saying that the charge density over here is larger than the charge density over here. I'm not saying that. I never said that. I never said such a thing.
I read it, like, for example, this area has rho, if you have rho here is longer than rho.
Okay.
For example,
You see, there was one reason why we never studied such pointed objects. We never study objects that don't have a certain symmetry, like rotational symmetry, spherical symmetry, etc. Because we don't have the mathematical tools to describe these things yet. You will study these things on your third year. Next year, you will be developing the mathematical tools. You will be learning your mathematical tools. And the following year, you will be applying them to study such phenomena. I don't have a simple explanation for this thing. I can calculate it. I don't think you would like to see the derivation of it. I don't have a simple one. We can discuss after the break, during the break. As I said, I will not explain it. I will just behave as if this question was not asked. Sorry. Just try this. Especially if you have a friend that has a long hair. Go to a kids' playground where they all have these plastic slides. And make your friend with long hair, preferably straight long hair, slide over those slides. I mean, you should better go at night, after dark. After she slides, or he or she slides a couple of times, you will see that all her hair is standing up. Because there will be static electricity built on her body, or her or his. And so the hairs, they will try to go as far away as possible from each other. So they will go just like this. And bring with yourself a pointed object. It has to be pointed. And just approach that pointed object to her hairs. And see what happens. Unfortunately, it doesn't happen with curly hair. But it happens with straight hair. Okay, give it a try, and then if you want, we can discuss it, what happens during the breaks. Not this break. We will have still 8 more. We still have 24 more breaks during the semester. Any other questions? We have a? Okay. So we have this shell. We place a charge plus Q on the center. Inside the conductor, there is no electric field. Okay.
At which point, or is there any point that we see some difference that the conductor cannot comprehend the charge inside?
Well, you see, we are still in electrostatics. And when that happens, we are no longer in electrostatics. So that's not our subject yet. Sure. But that limit will be very hard to reach, if possible. Okay, see you on tomorrow.
Hocam translation'larla ilgili bir soru var.